Okay, welcome everybody to the Joy track for Scala Love. For those participants joining us on Zoom, please feel free to ask any questions using the Q&A option that's on your client. That's the Q&A option, and I'll be asking those to the speaker at the end of the talk if we have some time. If not, don't worry. I'll also be posting a link to a breakout room that our speaker will be joining after the talk. So if you have any more questions or anything you just want to speak to them about, feel free to join that at the end. And now it's my great pleasure to announce our first speaker for the day, Lee Haoyi. I'm sure many of you already know Haoyi, but he's a major contributor to the Scala community. He made many popular open source projects such as Ammonite Scala REPL and the Mill build tool. Haoyi has used Scala professionally to build distributed backend systems, programming languages, high performance web applications, and much more. And today, Haoyi is going to be taking us through Mill, a build tool based on pure functional programming. Lee, are you okay to carry? Haoyi, are you okay to carry on?
Hello. Yeah. Sorry, let me get set up here. One moment. Okay, you guys can see the screen.
Yep, we can see it.
Okay, cool. So hi everyone. My name is Haoyi. This talk is going to be about Mill, a build tool based on pure functional programming. So I'm currently working at Databricks. We are a heavy user of Scala, the Bazel build tool, millions of lines of code in a bunch of different languages and frameworks. Previously, I was at Dropbox, and throughout this whole time, I've been doing a bunch of open source work. So many of you have used tools like Ammonite, Mill, FastParse, Scala tags, etc. I'm curious, how many of you guys are using different tools? Like, can you comment in the chat? Let's see, like, who's using Ammonite, who's using Mill, who's using Scala tags or FastParse? How do I see the chat? Chat. I don't know how to see the chat. I see someone on Twitch is using Request Scala. Someone else using Ammonite. I guess lots of people like Ammonite. Glad you guys like it. So let's move on. So the agenda for today is we'll cover what's a Mill build tool, what's functional programming, how a build tool is similar to functional programming, how a build tool is not similar to functional programming, and how the Mill build tool uses functional programming. So first, what is the Mill build tool? So Mill is an embedded Scala library built on top of Ammonite Scala scripts. It's heavily inspired by FDT, Bazel, Scala RX, and other things. Mill was not built in a vacuum. It's built on top of many other previous projects and made great strides forward. And to a large extent, it's just plain Scala. There's a bit of a star there. It does a few funny things, but by and large, it is just plain Scala. So if you look at a simple Mill build, it looks something like this. You have a build.sc file, some imports. I define an object that extends a module and define a Scala version. So this object foo creates a module in the foo folder, sources in foo/source. There's a resources folder in foo/resources, and so on. And I set the Scala version to 2.13.1. So this gives us the ability to run mill foo.compile, foo.run, foo.assembly. And these commands do everything a modern build tool should do. So if I run foo.compile twice in a row, I don't change the sources. It will not recompile because it's already ready. If I then run foo.run, it does not need to recompile because it's already ready, and it'll just run it straight away. If I then change the source code and run foo.run again, it will then recompile automatically before running foo.run, before running your application. So this kind of incremental computation, where it only does as much work as it needs to do, is crucial for any modern build tool, because many of these compilation steps, minifying steps, tree shaking, bundling, all of these are slow, and you do not want to do them more than necessary. Mill also supports test suites. So in this example, we are adding a test module here, object test extends test. It's just another module, which is this object is another module within the foo module, and it lives in foo/test. The module is in foo/test. The source code is in foo/test/source. And to make the test work, I need to add a test framework and define which test run I'm using. And this gives us the ability to use mill foo.test, mill foo.test.compile, foo.test.assembly, and so on. Mill supports multi-module builds. So here we have an example of 3 modules which share the same configuration. So configuration is defined as a trait app module, extends Scala module, and I have object shared extends app module, object foo extends app module, which depends on shared, And object bar extends add module, which depends on shared as well. So this gives us a small dependency graph with 3 modules, 2 of which depend on the shared module. And I can compile, run, and assemble all of the modules independently. And it automatically gets wired up. So if I compile foo, if shared is not yet being compiled, it will compile shared. Mill makes it very easy to wire up things. For example, let's consider a bit of an awkward use case. I want the foo module to have the bar module's assembly jar, like the self-contained Uber jar, as a resource. Why might I want to do this? Maybe I want to deploy it to a different server. Maybe I want to write it to a file somewhere and then execute it as a subprocess. So I don't want it as a dependency in my class path program and my program, but I want it as a file I can go chuck somewhere. So Mill makes it very easy to just override the resources and copy the file in. And after that, when you bundle foo, when you run foo, everything will be taken care of automatically. So I'll go into a bit more detail what this syntax here means in a moment. What does Mill do? Mill does everything a modern build tool does. And for JVM, that means I resolve dependencies, I compile source code, code generation, test things, zip things. All of this, all the things that SVT does, Mill also does as first approximation. Mill does not depend on SVT. Mill just re-implements all of this from first principles. It turns out that zipping files into jars and shelling out the Scala test to run your tests is not a particularly challenging programming problem. You just implement it and it works just fine. So why is Mill interesting? First, because Mill is fast. So Mill uses a background daemon by default, which keeps the JVM warm and responsive. And so when you run commands at the command line, the response times hover around 200 milliseconds or so of overhead. And because the JVM's warm, compilation's fast, bundling is fast, everything is much faster than many other build tools. Mill has out-of-the-box functionality, meaning that you can do a lot of what you need without any plugins. What do you need to do? You need to compile things, you need test things. How do you deploy a thing? You want the Uber jar executable assembly? Mill gives you that. You want to publish something to Maven Central? Mill gives you that too. No plugins required to provide everything you need. And everything's a bit of a star. Obviously, depends on exactly what you need. But Mill provides a lot of things built in without needing to fiddle with plugins. Mill is pretty well battle tested. So this is not just a case of, oh, this might work. Mill's used heavily in a lot of big projects. Like my biggest project, I think, is Ammonite, which due to all the cross builds has 179 Scala modules within it. And I can run them all, compile them all, test them all, publish them all. Now we just got the ability to do it in parallel. You can see 8 cores or 20 cores running in parallel, compiling Scala in this huge multi-module project. Mill supports Kotlin, Java. I use it for my blog. You can incrementally generate your static blog for you or static website. You can construct asset pipelines in the web. Maybe you need a version file layout with content address hashed file names. You can do that in Mill and have it cached and incremental for you. Or you can do things like construct PDFs. There's a Apache PDF box Java library. Just import it into Mill and you can start constructing PDFs as part of your build. So the thing that's most interesting about Mill, I think, is that it's intuitive and trivially customizable. So the point of Mill is that you just write plain old Scala. So within each build step, just write your Scala code, create your files, compute your values, and all the other stuff you get for free, like caching, file watching. Now you get parallelism in the latest master. Your code does not need to care about that, but you can just write plain Scala and you get all the good stuff. And I like this quote from Rex Kerr, which says, "I am so happy every time I have to tweak a little build stuff and find that my project uses Mill. Build system easy mode for the win." So I haven't seen anyone else say this about other build tools, but people do say it about Mill. It is really quite a nice tool to use and makes things really easy. So that's a lightning summary of what Mill is. I didn't go into usage documentation. There's a lot of documentation online about how to use it to do various things. This is a summary of what more or less Mill is and why you should be interested. Next, what's functional programming? Before we talk about what's functional programming, it may be worth discussing what are functional programming languages. These are a bit less contentious. So everyone agrees that Haskell is a functional programming language, or Camel, Clojure, Scala, F#, Scheme, all of these are functional programming languages. If we agree that all of these are functional programming languages, what do these languages have in common? So it's not really macros or metaprogramming. Sure, Scala has macros, but they're not the main thing in the language. It's certainly not parentheses because Haskell or F# don't have it. It's not type systems. Most lists do not have a type checker. They're untyped. Not all the languages use monads. Not all languages are going full-on writing interpreters within interpreters like the Scala or Haskell folks do. In fact, if you look at most interpreters, the Python interpreter is written in C, the Ruby interpreter is written in C. So that's probably not something specific to functional programming either. And what about constructing programs at runtime to execute? That sounds quite high level and fancy, but I've been doing that since 2010 in PHP templating my JavaScript. That was not a great experience, and it's not the same joy you get from functional programming. So what do I think functional programming is about? So as an example, I'm going to use a case study, which is my favorite tiramisu recipe, Michael Chu's classic tiramisu from the Cooking for Engineers website. So this recipe comes in two representations. One is a traditional imperative sequence of steps. So we begin by assembling the ingredients: 4 large egg yolks, half a cup of wine, 2 tablespoons of sugar, etc. You whisk the egg yolks, pour them in sugar and wine, whisk them again, step by step until you finish it and you have a tiramisu. Represented in pseudocode, I'm using Python-like pseudocode for now, it looks something like this. Make tiramisu, do a bunch of steps. In the end, I return the eggs, which after being mangled so much, they are now a tiramisu we can use. So what's wrong with this? Well, this works, and it's on the website. You can use it. You can follow the recipe. But the difficulty comes if you want to change the recipe. You want to refactor the recipe. Why would you want to refactor a tiramisu recipe? But if you have 2 people to work on tiramisu, can you make it faster? What can you do in parallel? Or what if after halfway through the recipe, I realize I bought the wrong kind of cream? I messed up. What do I need to do to recover? Do I need new ingredients? Which new ingredients? And what steps? Or if I spill the bowl on the floor halfway, a bunch of my ingredients are gone and I need to repurchase them and reassemble them. What do I need to do? So these are all questions that you can answer from this representation, but it is non-trivial. But realistically, you often have to do it if you're in a busy kitchen with many things happening and you want your dinner to come out as soon as possible. Michael Chu's classic tiramisu has another representation, which is kind of like a flow chart. So it says, well, I start off with egg yolks, granulated sugar. I beat the egg yolks, beat them with the granulated sugar and masala wine, whisk them. Then I beat them with mascarpone cheese. Then I fold them into the heavy cream, and et cetera, until you refrigerate it. And on the right side comes out the tiramisu. So if I look at this as a graph, this is basically like a data flow graph, or maybe you can call it the food flow graph of where the food is going and where the tiramisu comes out on the other side. And if you represent this as code, it might look a bit like this. So this is a bit of an awkward, like nested function calls code. But if you draw the arrows of where all the variables are going, you'll see that this graph that appears here is exactly the same as a graph that appears here on the flowchart. It's just in a slightly different direction. And it's a straightforward matter to just assign local variables to the intermediate computations, give them names, and you end up with quite a reasonable looking piece of code. Except now, instead of having an imperative piece of code, I have a functional piece of code. So imperative versus functional, they kind of look the same. What's the big difference between them? So imperative code is a sequence of steps, while the functional code is kind of a dependency graph of steps. So in imperative code, it's usually unclear where the ordering matters, where it doesn't. And anyone working in a large imperative code base has seen a problem where, oh, I reordered 2 statements and some weird thing happened because the ordering mattered, but I didn't figure that out. Whereas in functional code, it's usually trivially obvious which steps must happen before which other steps. If I compute a variable and I pass it to you, then clearly I must happen before you. And if your computation output gets passed to someone else, you must happen before them. So in imperative code, the dependencies are implicit in the ordering, while in functional code, the dependencies are explicit in the structure of the graph. Whether it's the data flow graph or the definition and identifier graph in your program, it's the same graph in the end. So coming back to refactoring, if I want to refactor this recipe to answer these questions, it's much easier. So although here I have a sequence of lines of code, it's straightforward to go back from that sequence to this data flow chart or this graph. And from this graph, it's trivial to see that, well, if I have multiple people to work on the tiramisu, these 4 sections can be done in parallel, no problem. Instantly, I can see this. If after I beat the eggs and cheese, I realize I bought the wrong kinds of cream, instantly I can see that I need to get new cream, re-whip the cream, but all the eggs, mascarpone, masala, wine mixture are unchanged, are still usable, and espresso and granulated sugar are also still usable. Lastly, if I spill the bowl after beating mascarpone cheese into egg mixture, what ingredients do I need to recover? I can just look, I messed up here. I go to the left up the graph. I need egg yolks, granulated sugar, masala wine, and mascarpone cheese. So We are thinking about dependencies between parts of your program rather than lists of steps to be done. That's what functional programming is about. It's about the data flow rather than control flow. So it makes things like parallelization, reordering, and incremental recomputation trivial. And this doesn't matter whether you're trying to incrementally recompile your Scala code or you're trying to incrementally reconstruct your tiramisu because someone dropped the bowl on the floor. It's kind of the same thing, and you need to do the same reasoning to get your answer. So while we often serialize a functional program, the dependency data flow graph into a linear sequence of lines of code, the core structure is a data flow graph. And anyone who looks at the lines of code will be able to figure out the data flow graph. Your compiler will take the lines of code, turn it into a data flow graph, and then compile. Your editor, your IntelliJ, will take the lines of code, turn it into a data flow graph, and then do the analysis. And you, the programmer, are probably doing the same thing in your head. And that's why working with functional programs is often easier than working with imperative programs. So next, how are build tools similar to functional programming? Here are a bunch of build tools from the Java ecosystem. We have Ant, the oldest one, Bazel, Pants, Mill, the newest ones, and SVT, Maven, Groovy in between. Java build tools all more or less do the same things. So these are things that Mill does. You look at Groovy, you'll have the same things. Look at Bazel, for the Java side, will have the same thing. SVT will have the same things. What's notable about these steps is that they all follow the same pattern. Resolve library dependencies to make dependency jars. Compile source files and dependency jars to make class files. Test class files and dependency jars to make test results. It's always do thing to foo and bar to make output. So not everything in the build tool matches this template, but I would say maybe 99% of the things the build tool does will fit this template. So things like Scala formatting of source files doesn't really fit. Things like uploading to Maven Central doesn't really fit, but most things will fit. And if I take this from English-like SQL or COBOL-like code and turn into, let's say, Pythonish pseudocode, it becomes this. Output equals do thing to foo and bar. I pass foo and bar to a function do thing, and it spits out an output. And this is exactly what functional programming is about. You take things and you spit out outputs, and there are no side effects. I'm not mangling them in place. I'm not doing weird things for network. Take inputs, spit out output. Take input, spit out output. Do the same thing over and over until you have a final output that you want to be able to use. It turns out that build tools and kitchens making tiramisu have often very similar requirements. A build tool may want to parallelize build steps so you can see your code running faster, and a kitchen may want to parallelize different cooking steps in order to get your tiramisu out the door. If someone changed the source file and I want to regenerate the artifacts affected, that's the same as someone changing one of the ingredients and having to reassemble the different components that I need. If someone wants to figure out, given these sets I want to run, which input files I need to watch, that's the same as saying, given this build step which I messed up, what are the ingredients which I need to recover from that, input ingredients. So although very different contexts, the requirements are actually very similar. So how are build tools similar to functional programming? Build tools are largely, with a star, largely made of pure functions. Output equals do thing to foo and bar inputs. And the ease of which functional programming allows refactoring, parallelization, analyzing, and computation is exactly what the build tool needs to do. So while functional programming helps humans do it and a build tool needs to do them automatically, it's really the same thing when you take some unrelated computations, run them on separate threads, or you take an incomplete computation and want to complete it without having to redo a bunch of unnecessary work. So we've seen what's Mill, we've seen what's functional programming. We've talked about how build tools like Mill, but others as well, like Bazel and others, are similar to functional programming. Let's now look at how build tools are not similar to functional programming. So if functional programming is so good and build tools are so similar, why don't we just write all our build tools in raw Haskell with no libraries? After all, it's a functional programming, right? Functional programming language, right? It turns out that build tools have some very specific requirements that are very poorly satisfied or not satisfied at all by naive functional programming. Build tools need introspectability. Build tools need persistence. Build tools need some kind of long-lived worker process daemon things. And build tools need ad hoc overrides. And we'll go into these one by one. First, let's look at introspectability. Consider this snippet from our earlier tiramisu recipe. I'm just going to use the first 3 lines. I beat the eggs, beat eggs, sugar, wine, and wine to make the mixture, and then I whisk the mixture to make the whisked mixture. So if this is a pure functional program, there isn't that much you can do with it as a program. Pure functions tend to be opaque. You can run them, and that's about it. You pass some parameters, they run, something comes out the other side. It's not like an object where you can look at the fields of an object, inspect the fields, reflect on this, reflect on that, maybe poke at some getter methods. Functional programs tend to be full of pure functions, and things you do pure functions, you run it, and that's about it. On the other hand, what does a build tool need to do? Build tools do not just run your entire build over and over. That would be exceedingly slow. Imagine if every time you wanted to change a line of code to add a print line, you had to delete every single compilation artifact and recompile the world from scratch. Now, that would be unacceptable. So build tools need to be able to inspect the structure of computation, to parallelize steps that can be parallelized and don't depend on each other, to incrementally recompute steps that are, without having to recompute the ones that are still valid. And if you're using something like mil-watch, SVT tilde, or a Bazel-watcher, you need to be able to inspect the graph to figure out what inputs to watch. I want to run these tests and inputs change. What are the inputs? I need to know. Next, persistence. Pure functions have the intermediate values live in memory. Beat, eggs, mixture, whisk, everything except the return value of this function lives in memory. And they either go away when they are garbage collected, or they will go away when the program terminates. This is very good if you want to avoid side effects, because there are these little things encapsulated perfectly in memory. No one else can poke at them, and you cannot poke at, and they cannot poke at anyone else. Great. Build tools are very different. Build tools need to have every output for every intermediate step serialized and saved somewhere, so that next time someone runs a build tool, we can reuse them. How are they serialized? Where do they get saved? We need to answer those questions. Maybe it's messy, maybe it's tricky, but if the decision is between waiting 1 hour to recompile universe from scratch or accepting a bit of messiness in the build tool, everyone will pick up the messiness. Everyone will choose the messiness in the build tool in order to reduce their iteration times. So the third thing, long-lived workers. Pure functions have no side effects and can be run any way we like. I can run them once. I can run them 5 times over and over. I can run them 100 times on separate threads or even separate processes. It doesn't matter, they're pure functions. Build tools, on the other hand, are different. The things that the steps your build tool needs to do often require some setup. The setup is often expensive. Maybe your JVM is cold, needs to warm up, takes 1 or 2 seconds. Incremental compilation caches in Zinc need to be populated. That takes a while. First runs will be slow. After that, it will be much faster. And your WebKit HTML to PDF worker needs to be spawned if you want to use this to convert some HTML pages into PDF. And all of these things are often expensive. You want to reuse things. And concurrency is often limited or disallowed. I cannot spawn 100 Scala compilers on my computer. It will explode. So I need to be able to limit it. There's no such thing as zero side effects when running out of memory is a side effect. Lastly, ad hoc overrides. So a pure function's parameters contain everything you need to do you can do to customize it. I can change what eggs I pass in. I can change what sugar one I pass in. I can change what wine I pass in, and that's about it. If I want to customize other things, I need to pass in flags. I need to pass in the egg beater I want to use or the whisk I want to use. But if I basically cannot configure anything that is not part of the function parameter list. So this is good if you don't want to configure things that often. And this is bad if you very often want to configure things. While maybe in production code, you don't want to reconfigure things all that often. Your production code is often quite elegant and straightforward. Your build code is usually very, very gnarly. And when you're working in the build system, the exception is the norm. Someone will need a custom artifact name. Someone will need special Java options. Someone will need a weird code generation step in order to convert their proto files into Scala source files. And they'll need a second code generation step to mangle the Scala source files with a weird vendored version of Scala PB. And some module somewhere is going to need to turn off incremental compilation because Zinc has a bug in it and we can't figure out why. So there is no elegance in this. Every module, not every module, but almost every module is going to need something special. They're all going to need something different. And we need, as a build system, need to be able to handle that in a reasonable way. So these are the 4 ways that build tools are not similar to pure functional programming. They need introspectability, they need persistence, they need long-lived workers, they need ad hoc overrides. And if you start writing a hello world program in Haskell, these are the 4 things you're missing to turn it into an awesome build tool. So what's next? We've covered what's a build tool. We've covered what is functional programming about, how build tools are similar, and how they're dissimilar to functional programming. The last thing we'll cover is how the Mill build tool uses functional programming, but also does some tweaks to it in order to satisfy all the requirements that any modern build tool has. So Mill basically takes the naive pure function on the left. Here I'm using Scala pseudocode. I'm not annotating the types of the parameters, but you know what I mean. I take this is the same as eggs. This is a make Tiramisu Python function I had earlier, but with some extra curly brackets and vals. And I convert it into a trait Tiramisu module extends module. So this is spelled a bit differently. It's a bit more verbose. The function parameters become t.input definitions in my trait. The val intermediate vals become defs which with t blocks. These are often called targets in Mill, using the same names terminology that Bazel uses. And references to eggs, beat eggs, sugar one, wine, and mixture become eggs parens, beat eggs parens, sugar one parens, and so on. So things are spelled slightly differently, and there's a small amount more syntax, but the fundamental structure of this Mill Tiramisu module and on the left side, this make Tiramisu naive pure function, the fundamental structure is about the same. So how does Mill use functional programming, but with these 4 requirements that we saw earlier? So first, let's look at introspectability. So Mill turns the build steps, again, and they're called targets, into a free applicative data structure using the t curly brackets macro. So if I compare these 2 examples, on the bottom, I have the naive pure function. On the top, I have the pure function, but the vals become defs. And the right-hand side of each def, there's a t block surrounding it. And each variable reference, eggs, becomes eggs to the parens. So what does this funny syntax do? So it's a macro, but it's a very simple macro that does something that you should be able to understand. This macro expands into this kind of t.zip map eggs v1 goes to beat v1, t.zip map beat eggs sugar wine v1 v2 v3 goes to beat v1 v2 v3. Different frameworks call zipmap a different thing. In Haskell, it's called app, just like AP. I think in CATS it might be called zipmap, or it's like the TIE fighter operator pipe at pipe. But basically this transformation is often called idiom brackets. Again, idiom brackets are not a new thing. If you Google idiom brackets in Haskell, you'll see there's much prior work around it. But the idea is that I can turn this straightforward looking code with a small amount of annotation around the important bits into this kind of applicative zipmap code. And in this case, I'm using a free applicative. So I'm not evaluating anything right now. It's not like I'm having futures and running them, or I have like an option monad and I'm propagating the option through the computation. What this free applicative zipmap does is it simply constructs a graph data structure. And every node in the graph data structure has a list of inputs and has an opaque function to compute its output value from its inputs. So notably, the structure of the graph cannot depend on the computed value of any node. So this is very unlike monads. If you do functional programming in Scala, everyone talks about monads. This is one step weaker than monads. In monads, if you're using a future, every time the future computes a value, you can use that value to decide what downstream computation to do, what downstream future you want to start, and so on. Whereas in this applicative or free applicative compute model, the structure of the graph is fixed up front. No matter what values come out of the beating of the eggs or the whisking of the mixture, the structure is as follows here. And this is very useful because it means I can completely ignore the computations and I can still do useful things to the structure of the graph. For example, I can introspect the graph to see what it looks like. Mill provides a visualize call, which will dump the graph to SVG for you to look at. I think Bazel does the same thing with Bazel query dash output equals graph. I think Bazel puts in it as a dot file. You can parallelize things by looking at which steps can happen in parallel and don't depend on each other. You can incrementally compute things by inspecting the graph, looking at where the values have already been computed and starting off from the places where they have not been. So these are all important things that the free applicative data structure gives us. And this is a very conscious choice. It's not that I just happen to anyhow choose a free monad because monads are what makes functional programming functional. I chose a free applicative because the free applicative gives us the ability to introspect the graph structure. And this introspection is exactly what a build tool needs in order to do its work. So that's enough about introspectability. Let's look at persistence. Every mil target defined via a T block, which is a target block, must return a type that is serializable. So in this pseudocode, I have def T. It takes in a type parameter V. The block can compute any value of type V, but that type V must be able to be readable and writable by upickle.default. And in this case, I'm using a upickle JSON like serializer, but it could be any format, doesn't matter. Upickle message pack, binary formats, Circe JSON, Jackson module Scala. The exact serializer doesn't matter. What matters is that the type of every target must be serializable. It could be a file can be written disk, could be a byte array. It cannot be an open TCP socket, because I can't just save an open TCP socket to disk and come back 2 weeks later and reload it. That doesn't work. What else do I need to do with it? Apart from how to serialize things, where do I serialize things? I need to store it somewhere. So every target, in addition to be requiring serializability, it also takes an implicit parameter mil.defined context, which contains a context or destination file system path. And what this does is that it is provided automatically for every target inside the module. So if I have a my Tiramisu extends module, the beat eggs target down here, this fellow will get automatically assigned a file system path out/my Tiramisu/beat eggs. Mixture will automatically get assigned a file system path out/my Tiramisu/mixture, and so on. You have nested modules, they correspond to nested folders on the file system. And this is important because it gives this context or destination path gives each target computation a place to put files on disk without risking collisions with other targets who may also be wanting to put files on disk. So remember that this is a build tool. We are compiling things, we are writing to disk, we are downloading things. You cannot avoid the disk when you're working within the build tool. And the problem with working with disk is that when you're working with a file system and I/O, often the problem is shared mutable state. I write to disk, someone else writes to disk, they stomp over my saved data, I get confused. I write over it again, I stomp over their saved data, they get confused. The shared mutable state is what makes writing to disk dangerous and sketchy. And mil does not get rid of the mutable state, but mil gets rid of the sharing part. Every target gets its own folder on disk, and every target can put things in the folder, save things in that folder, read things from that folder. No other target can interfere with it. And that's how mil makes file system I/O and persistence relatively safe, despite the fact that we are still reading and writing huge amounts of data to a shared file system. The third thing that mil needs to provide is long-lived workers. So mil provides a t.worker syntax. In this example, I am removing the hard-coded beat function, and I'm instead instantiating an egg beater worker that may be computed from somewhere earlier and using egg beater to beat eggs. So workers are similar to targets in that they can take inputs. You can pass in parameters to your worker. Your workers get invalidated if upstream targets change. But the difference is that workers, rather than being serialized and saved to disk, are kept in memory and last as long as the mil process lasts. By default, mil keeps a background daemon running, and the worker could last for hours. But even if you use mil in batch mode, the worker could still last several hundred compiles while compiling a large project before being shut down as the process exits. What do you put in a worker? Workers could be things like the Scala compiler. You want a Scala compiler to be kept in memory and hot? Well, you put in a worker. You can't serialize a warm Scala compiler to disk, right? What if you're managing a subprocess? If I'm generating PDFs, I'm using WebKit HTML to PDF binary. That binary has a significant amount of overhead that can be reduced by keeping it warm in memory in daemon mode using some flags. And who's going to manage the daemon? I can use an in-memory worker to manage it. And in effect, depending what what background you're coming from, workers are kind of like objects or kind of like first-class functions, in that you can instantiate them with parameters and then pass them around and call them on other things. The only difference between workers and objects and first-class functions in traditional object-oriented functional programming is that workers enjoy the same automatic invalidation that all targets do in Mill. But otherwise, Mill effectively has a first-class functions as part of the build system, and it works great. And this was the idea I stole from Bazel from my experience working with Bazel at Databricks. I guess before I go into ad hoc overrides, one more thing to mention about workers is because I can compute workers as part of the build system, it means that I do not need to hard code like environmental variables or environmental logic in order to do things. Let's say I'm running Mill, but I do not have a Scala compiler. Why do I not have a Scala compiler? Let's just take it for granted. I do not have a Scala compiler. Well, I could have a Mill target that downloads a Scala compiler from the internet from Maven Central. I could then spawn a worker that will then run the Scala compiler in memory, and I can then use that worker just to compile anything I want in my build system, similar to any other piece of logic I download. So in a build tool like Mill or Bazel, which Mill is inspired by, compilers, workers, linters, packaging tools, these are not special. These are just another target. Maybe they are worker processes, maybe they're not, but they're just another thing that you build as part of your bootstrap process as you go from nothing to a complete application. So that makes, if you don't like the Scala compiler that Mill provides, download your own, download the Dotty compiler. You want to compile Kotlin, go download the Kotlin compiler, put in the worker, and get to work compiling things. This is quite unlike SVT, where compilers and such are these magic environmental meta plugins that behave very differently from most of your SVT code. In Mill, compilers are just another build step, and they're kind of like a first-class build step, and they use them in downstream build steps. Someone on Twitch said they want to work for running a local DynamoDB instance. I don't know if DynamoDB can run locally, but I personally use workers to run local Postgres instances using the org.opentable.postgres test Postgres packages, and it works great. Next, let's go to ad hoc overrides. So sets of similar build steps in Mill are constructed using traits rather than functions. And what's useful about traits is that you can override anything you want in them. So I've eggs, sugar, wine as inputs. I beat eggs. I beat the eggs, sugar, and wine. I whisk the mixture to get the whisk thing. I can pass in different eggs, sugar, and wine. But I could also pass in a different step of beating the eggs. Maybe I want to use pre-beaten eggs from a carton. Maybe I want to whisk things differently using, instead of whisking using a whisker, I want to put in the bottle and shake it. There are all sorts of weird ad hoc things that you have to do in any real build system. And it's no good to like shake your finger at someone and say, no, that's bad, you can't do it. Someone is going to need to do it, and the only question is how painful is it going to be? And so Mill makes it easy for you to override things in your build. You want to change this here, change things there, it's okay. We are all adults here. We will let you do it in an easy and straightforward manner. So that's how the Mill build tool uses functional programming, but with a side addition of introspectability, persistence, long-lived workers, and ad hoc overrides. And these are the things that stand between a pure functional program and a high-performance, convenient, intuitive build system. So what have we talked about? We've talked about what's a Mill build tool. We've talked about what's functional programming, how build tools are similar to functional programming, how build tools are not similar to functional programming, and how build tools use how the Mill build tool in particular uses functional programming plus other cool things in order to do its magic. So what are the main takeaways? Functional programming is thinking about data flow rather than control flow. And this data flow graph is what makes refactoring, parallelism, program analysis, all that way easier than an imperative step-by-step side effecting program. Things like monads, things like monadic interpreters or finely tagless, these are cool things you can do using functional programming, but they are not the core of what functional programming is all about. Functional programming is about data flow. And if you do a survey of the common functional programming languages, it's about the data flow. Build tools are also all about data flow. And these benefit from all the same things that humans enjoy when using functional programming. Build tools also need parallelism, refactoring, program analysis, introspection, all those things. But build tools have additional concerns that naive functional programming satisfy not at all. Build tools need introspectability, build tools need persistence, build tools need long-lived workers and ad hoc overrides in order to turn them from something that's a batch, inefficient batch process to an incremental, parallel, efficient build tool. And Mill uses a mix of functional programming and object-oriented features to get the best of both worlds. So Mill uses the free applicative data structure with idiom brackets in order to give us introspectability into the program graph. Mill uses the Dataflow graph Mill uses a program graph in order to give us the nice refactoring and parallelism analysis. But on the other hand, Mill also uses traits in order to give us the ability to template our build system. We have many modules with the same similar tasks to perform, as well as to let us override things ad hoc, because that's something that build tools often need to do. So we did not use these things randomly. It's not that, oh, I need to be functional programming. I'm just going to go and pick up a random category theory concept and use it. But I picked the free applicatives and traits specifically because these are the things that give us the tools we want to satisfy our build tool requirements. And as a result, Mill gives us code that's easy to read and intuitive as pure functional programs for the speed, efficiency, and feature set that people expect from a modern build tool. And that's how you get to build system easy mode, as one of my friends like to call it. So that's Mill, a build tool based on pure functional programming. One thing you may have noticed is I talked about compiling PDFs using Mill. That's something I've been working on recently for a while, and it works surprisingly well. You can use Scala tags to render HTML. You can render Markdown using the Atlassian Markdown library, and you can render PDFs using WebKit HTML to PDF. And I've been doing this because I've been writing a book called Hands-on Scala Programming, which, apart from Mill, covers a whole bunch of other things to give you a practical project-based intro to Scala. So if you like what you saw in this presentation, you like the philosophy, you like the down-to-earth practical approach of doing things, you can go take a look at the website. It's not yet ready yet, but there's a subscription link for you to subscribe if you want to be notified when it's ready. It'll be done in a few months, sometime in summer 2020. So that's the talk, and I will take questions, I guess. How do I take questions? Q&A?
Yeah, hi, Haoyi. Thanks very much for the talk. I'm sure everyone agrees with that. It was a very comprehensive overview of Mill. I don't know if you can see the QA section, but I'm more than happy to read out the questions if you can't.
Could you read it out? It doesn't want to open for me. I'm clicking on it.
Of course, no worries. So the first one, quite an involved question, actually. So you explained that the target graph has a free applicative structure, and the structure can never depend on the values of the inputs. This question is like, so sometimes we do need to escape that mechanism, and in SBT there is the mechanism for the normal applicative structure. Is this something that Mill does support, and if yes, kind of how?
So the normal applicative structure also cannot depend on the value of the structure of a normal applicative also cannot depend on the value of its inputs. SBT goes beyond that and allows some like monadic structures where it does depend on the value of the inputs. Mill does not support that. So what Mill lets you do is that if you look at this bit of Mill code here, whether the macro-based version or the desugared zipmap-based version, we are constructing the graph at runtime using Scala code. So as part of constructing the graph, we can run Scala code before the graph is constructed in order to decide what we want the graph to look at. And this is used, for example, for cross builds. Maybe you want one module per folder, and a cross build lets you do that in an easy manner. But once the graph is constructed, the shape is fixed. So you effectively get a two-stage computation. One stage, run whatever Scala code you want, and then it constructs a graph. And the second stage, we do this incremental thing over the graph in order to give you a final output. And in the vast majority of cases, the first stage is trivial with not much logic going on. But you can put logic there at the cost of maybe slowing down every Mill command, since you have to reevaluate that code more frequently. This two-stage architecture is a similar architecture to how Bazel works, for example, which also has separate analysis and execution phases. I think that answers the question.
Yeah, okay. So I think we've got time for one more question at least. Someone's asked, what's the overhead of the Mill daemon in terms of like threads, memory, CPU?
I think it's basically up to you. There's like a bash command which spawns it off. It passes in some parameters. I don't believe we customize it, so it probably just uses the default JVM settings on your computer, which works okay. If you want to give it more memory or less memory, I believe there are flags you can pass in to adjust its configuration.
Okay, cool. And another question is it possible to set up multi-project with Mill, with one of the sub-projects being a Scala JS project?
Yeah, so if you go to the Mill documentation, I believe there's an example with Scala JS. If there isn't, you can go look at some of my projects. For example, the Fansi library, FANSI. That fellow is a very, very small one-file Scala JVM, JS, and native project. And you can see how the cross-build and stuff works. You can also do like client-server style Scala JS, Scala JVM projects as well. And we can help you out in the Gitter channel if you need help.
All right, cool. Well, thank you very much again. I'll give you some applause since everyone else can't.
Cool.
I've just posted a link to the Q&A room in the chat on Zoom. If you could please go into there, I think one of the other track owners is going to be in there to help you out. And if anyone has any extra questions, then they should be able to go and see you there.